Hello everyone, and welcome back. Last time we finished up with Newton's laws. Today we're going to start section 5, additional applications of Newton's laws. For some reason, textbooks often separate these into two different chapters. The first one, introducing Newton's laws and some examples, and the second one, more examples. So we're just going to look at some more examples of Newton's laws. The law that I want to start with today, not one of Newton's laws, but a different law, also from Newton, as a matter of fact, a new force, not a new force, an old force, but we're going to look at it in much more detail. This is Newton's law, or Newton's universal law of gravitation. So we're going to be looking at gravity. But what does this mean to be a universal law? Well, when Newton introduced this, he wanted to emphasize a very, very important point about gravitation, that it was universal. In other words, it operated in the entire universe, as opposed to previous ideas that worked either in the terrestrial realm here on Earth or in the celestial realm up in the heavens or with bodies in the skies. Newton wanted to emphasize this law worked everywhere in the universe. Universe coming from the Latin unus versus, turned into one. So we're joining up the terrestrial and the celestial realm into a single object. Everything in the universe, everything now is in the universe, and this law applies then everywhere. According to Newton. We'll see later on where this might not exactly work. What Newton's universal law of gravitation states is that every particle in the universe, every particle, attracts every other particle in the universe. So let's imagine we've got two objects, one with mass m1, one with mass m2. What this states is that they are attracted to each other. We will call the force on m1 F12, the force on particle 1 from particle 2, and then F21, the force on particle 2 from particle 1. There is a force of attraction between them. This force, these two forces are equal, so F12 equals F21, which we would expect from what? Newton's third law. For every action there is an equal opposite reaction. So we would expect these forces to be equal. But also, they are both proportional to the mass of the first object, the first particle, m1. They are also proportional to the mass of the second object, m2. But they depend on the distance between the two. So let's imagine the distance between them is some distance r. So be careful. There's a tendency to always think of r as a radius, but in this case it is not. It's not like half the distance or anything like that. Be careful about that. R is just the distance between the objects, and to be precise here, let me emphasize this would be measured, measured center to center. In other words, from the center of mass 1 to the center of mass 2. That's a very qualitative term right now. What do we mean by the center of an object? We'll talk more about that later, the center of mass of something. But just for now, let's imagine r is the distance measured from the center of m1 to the center of m2, and it turns out then that the force is proportional to 1 over the distance squared. So as r increases, the force decreases. As the distance between them gets larger, 1 over r squared gets smaller, so the force gets smaller. When we look at larger masses, if we increase one of these masses, the force would increase, both the force from the other mass and also the force on the other mass would increase by increasing one of the masses, and likewise increasing the other mass. There is then a constant of proportionality, which we're going to stick in here to make this a single equality equation. Let me just erase this and I'll write this down. So what do we have? The force of attraction, and I'll just write it as F because it's the same magnitude of force on each one, although the direction is opposite, is equal to mass 1 times mass 2 divided by the distance squared, and then the constant of proportionality we call capital G, or big G. This is literally referred to as big G. Not to be confused with little g, right? Little g, while little g also has to do with something to do with gravity. It's the acceleration due to gravity near the Earth's surface. Remember, it has a value near Atlanta, 9.80 meters per second squared. Okay, there we go. Now, what is big G? Big G has a value of 6.67 times 10 to the minus 11th, and then the units to take, multiply by kilogram squared, divide by meters squared, we must get units of newtons. So the units are Newton meters squared per kilogram squared. Those are the units of big G. All right, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Let's stick some numbers in here and see what we get. Because Newton's law applies to any two objects in the universe, you can pick whatever you want. I happen to have two little masses here. I've got a 10 gram mass and a 50 gram mass. And let's imagine that we put these 50 centimeters apart. So I've got a 10 gram mass here, 50 gram mass here. So 50 centimeters apart, about half a meter. Or, well, that would be exactly half a meter, right? So here, I've actually measured this, so that looks just about 50 centimeters. Okay. So we've got these two masses, 50 centimeters apart. Newton's law tells us that there is a force of attraction between them. They are being pulled together. I don't seem to really feel much. Let's do this calculation. So what do we have? We've got the force of attraction is 6.67 times 10 to the minus 11th. Whoops, and I forgot to put the units in there, haven't I? This would be Newton meters squared per kilogram squared. Times m1, let's put them all in standard SI units right in the beginning. So 10 grams would be 0.0100 kilograms. So times 0.0100 kilograms times 0.0500 kilograms divided by 50 centimeters, or 0.500 meters squared. Now let's notice the units. See, these work out. We've got meters squared. They cancel meters squared. We've got kilogram times kilogram, kilogram squared, cancel kilogram squared, and we end up with newtons. There we go. All right, very good. So what do we get when we multiply this out? We get 1.33 times 10 to the minus 13 newtons. In other words, 0. I think that's right. Whoops, got one extra in there, I think. There we go. That's the force. 0.00000000000000000000013 newtons. That is a very, very small force. The gravitational force, as actually we mentioned before, remember when we were talking about the relationship between the gravitational strength and the strength of the electromagnetic force, the electric force of repulsion between two electrons? What did we find? We found that the electric force was so much larger than the gravitational force. Well, here we see again that with two ordinary everyday sized objects, the force of attraction is extremely small. Would you be able to notice this just holding these? Absolutely not. It would take some incredibly sensitive instruments to notice that force. So what is this telling us? Well, what it's telling us is something very important, that the gravitational attraction between normal, everyday sized objects is not something that we are typically going to notice. It's a very, very weak force, and the only way that we will notice the gravitational force is if at least one of these objects is very, very large, a large mass, to increase the force enough that this product then gives us something that's relatively bigger. Well, what kind of thing? Well, what about the Earth? Let's take a look at an example of the attraction between the Earth and an object and see what we get in that case.